Welcome to the second session, which again is on number systems and codes. Today we're going to look at the hexadecimal number system, which is fundamental to our understanding and use of binary number system. This session will build on your previous knowledge on binary numbers by looking at hexadecimal systems with relevant conversion between the described number systems. The session also covers signed numbers and their representation, as well as digital codes and error detection in using codes. So, you should be able to express binary numbers in different formats, carry out arithmetic operations with signed binary numbers, convert between binary and hexadecimal numbers, express decimal numbers in binary coded decimal form, convert between binary systems and gray codes, and explain how to detect error codes, and discuss the cyclic redundancy check. These are things you should learn or be able to, we want you to know, or I want you to know. It's not everything that I'll cover in detail, but So what are the key topics? There's an octal number system, the hexadecimal number system, the conversion from octal to binary, and conversion from hexadecimal to binary, and then binary arithmetic operation with signed numbers, and then the codes. Those are the key things that you need to learn and know in this session. Again, the recommended test is from Fundamentals of Logic Design, chapter 1 of that, and chapter 2 of the book on Digital Fundamentals by Floyd. So the octal number system. So the octal number system is made up of octal digits. That is 0, 1, 2, 3, 4, 5, 6, and 7. Note that whenever we talk about a certain number system, that digit itself is not represented in the system. So in the binary number system, for example, we had the digits 0 and 1. 2 itself was not represented. So you can note that in the octal system, the digit 8 is not represented. So you have 0, 1, up to 7. So if I mention, let's say, a number system that based on 5, it means the digit 5 would not be represented there. So how many items does an octal number system represent? An octal number represents? Well, basically, it means that you have power 8 now is your base, so 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, 8 to the power of 3, and you multiply by the digit that is found in that position. The same way you do for the decimal parts. So the octal numbers wouldn't use the digits of 8 or 9. Now, who would use the octal number system anyway? Why do you want to use that? It's a question you should think about. To convert between the numbers, so you must learn to convert between the bases. And I said earlier on in the first session that to do this conversion, it's always best to convert to the binary number system first, before converting to any other system. In the hexadecimal number system, we now have 16 digits. So we have a 0 up to 9, and then 10, we use an A to represent a 10, B to represent 11, and up to F, which represents 15. How many items does a hexadecimal number represent? Again, the same way, this time is 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, and so on. And then you multiply by the appropriate number in that position. And fractions are done in the same way, 16 to the power of minus 1, 16 to the power of minus 2, and so on. Now, it is good to note right here that you can use a hexadecimal number digit to represent a group of 4 bits. So every nibble you can represent with 4 bits, 4 bits, using one hexadecimal number. So for example, if you have 1110, which is 14, that is an E. 1110 in base 2, which is 14 in base 10, you can represent that as E in the hexadecimal system. Now, the conversion between binary and octal and hexadecimal. So it's quite simple. all you do is group these numbers into twos, into fours, group them into fours, put them into groups of 4, and then you convert them. So let's say you have the hexadecimal number 3A9F. Well, so first convert the 3, which is 0011. A is 10, 1010. 9 is 1001. And F is 111. So then that's easy, straightforward. So you determine the 4-bit value of each hexadecimal digit. Now, I asked the question, why would you want to represent, numbers using hexadecimal or even in octal? If you haven't thought about the answer, it's quite straightforward. It's because it's easy to read and write. Now, how do you convert between a base 16 and a base 8? Again, it's quite easy. Put them into groups. Convert the hexadecimal number into binary, right? Once you've converted into binary, group them into 3s. Put them into groups of 3. Starting from the least significant bit. And then once you've done that into groups of 3, you convert them, into the base 8. So convert from base 16 to base 2, regroup the bits into groups of 3, starting from the rightmost, that's the least significant bit, and then you ignore any other leading zeros. So how do we do binary and arithmetic operations with signed numbers? Right, so the first thing is to do the conversion, indicate the positions. So for example, you have a 1100101 in base 2. It's a signed number, so you have a 0 there to represent the sign. So you add, because those are 1, 2, 3, 4, 5, 6, 7 bits as it is. And then so you add an extra bit to the left to indicate the sign. And then once you have that, you have your signed number. If it's a negative number, then you put a 1 in that position. We already came across this, that there are 3 ways in which you could represent, signed numbers. So you have the sign and magnitude, the 1's complement, and then the 2's complement. So to get the 1's complement, we said you invert all the bits, So the 1's complement of a number is, you have the binary number, and then you just simply change all the zeros into 1's and all the 1's into zeros, and that is all. The 2's complement, to find the 2's complement, you first find the 1's complement and then add 1 to the least significant bit. Yeah? So finding the 2's complement involves first finding the 1's complement, yeah, and then adding a 1 to the least significant bit. Well, if you're using 1's complement, adding again is straightforward. Supposing you wanted to add 1100 to 0001, so that 1100 is actually a 12 in base 10, and then the 0001 is a 1 in base 10. So if you add that, your answer should be what? 13, isn't it? So you write down the 12, and then if you did, the 12, the 1's complement, is 0, because you need the sign bit, 0011100, and then the 1 or so, you write them down, and you simply add the numbers as they are. And, it's straightforward. What about subtraction? Remember that the 1's complement, you have a sign bit in which you must put a number there, a 0 or a 1, to indicate a sign. Now, if you are doing a 1's complement subtraction, then you wanted to subtract 1 from 12, okay? So, because the 1 now you are subtracting, that 1 is a negative number. So the 1's complement of it is to convert all the numbers into what? Into the opposite. So you change them. So it means that you have your 0, 1, 1, 0, 0, and then you then add the 1's complement of the minus 1, because you are subtracting 1. If you did that, then you have 0, you have 0 and a 0, 0, 1, 1 and a 1, you carry the 1, and you add the 1 carry over to the end, so then your final result will be a 0, 1, 0, 1, 1. You know, this is something you should work through on your own to see how actually it operates. So there are three steps. First, take the ones complement of the second operand, add the binary numbers. If there's a carry, add it to the lower order bit. So take the ones complement of the second operand because we are subtracting. Take the ones complement of the second operand, add the binary numbers, and if there's a carry, add it to the lower order bit, so that to the least significant bit. The same thing, if you want to use two complements addition, you know, well, if the numbers are all positive, you write down the two's complement of them, and then you add, and you know, you don't have a problem. Now, if you wanted to do subtraction in two's complement, again is the same thing, because you are doing a two's complement subtraction, you needed the number to be negative. So you convert, you take the two's complement of the second operand, that's the one you are taking off, you know, you are subtracting, add the binary numbers, but this time you ignore the carry bit. So in the ones complement subtraction, you add the carry bit to the least significant bit. In the two's complement, you ignore the carry bit. So there are a number of examples you can work through yourselves. You know, the key thing is, so you want to subtract, let's say 13, you want to subtract 5 from 13, you know. Right, you write down the 13, the binary form of the 13 with the sign. Now, since it's going to be a two's complement, subtraction, you write the negative number as a two's complement, right? Add the numbers, there's a carry, you ignore it. So there's another example where you take away 12 from 5. So you can work through this and verify for yourselves that the answer will be what? A -7. Right, codes. What are codes? In communication and information processing, a code is important to carry, you know, the information or rules to convert for converting the information. So you may be a letter or a word or a gesture, so you convert from one form or the other, you know. And decoding is a process of going back the other way. So encoding or coding is a process of what? Converting the information from one form to the other. So you convert, so all that we've actually been doing is one form of encoding. So for example, when we change from binary or decimal to binary, we're actually coding it, you know. So, but the key idea is that the coding here is being used in a slightly different sense, you know, in the sense that we need to send information across, transmit information from one end to the other. And it's important to sort of put the information in a form that will make it not liable to be affected by the medium through which it's being sent. Because normally the medium over which this information is sent is noisy. And therefore it means that the information can become distorted as we transmit it. So we needed to code it in a way or change the format of the information so that it will not be affected by the noise. So coding would facilitate, you know, efficient transmission, error detection, and correction. So coding is a process of what? Altering the characteristics of information to make it more suitable for the intended application. The coding schemes, there are different coding schemes, and they depend on security requirements, the complexity of the medium of transmission, the levels of error that is required, and also the need for standardization. There are various forms of codes that you come across, but the most common ones that you should know about are the binary coded decimal, ASCII code, gray code, and error codes. Yeah, these are the form of codes that you should know and read about. The binary coded is the most simplest, right? In which case, each digit is given a binary equivalent. A decimal is given a binary equivalent. So in the simplest form of binary code, each decimal digit is replaced by its binary equivalent. So 9, for example, in this example, is replaced by the binary equivalent, which is 1001. 3 is replaced by its binary equivalent, which is 0011. And 7 by its binary equivalent, 0111. The 2 on the decimal part is also replaced by its binary equivalent 0010, and the 5 by 0101. Then there's the ASCII code. ASCII stands for the American Standard Code for Information Interchange. Now here they use 7 digits of 7 binary digits to represent all forms of things. So, for example, if you have on your keyboard, the space bar, when you press the space bar, actually what you are bringing up is a code of 010000. If you use an exclamation sign on your keyboard, the code for that is 01000001, and so on and so forth. A capital A will be 1000001. So all the characters that we have are given special codes. Yeah, and these are the codes that you normally find on your keyboard. This is called the ASCII code, or the American Standard Code for Information Interchange. And then there's another code known as a gray code. Yeah, there's the 3-bit gray code, the 4-bit gray code, and so on, right? Now, the thing about the gray code is that in a gray code, what you realize is that all the bits, one bit, if you move up the decimal number, say you move from 0 to 1, then from 0, the 3-bit gray code for 0 is, say, 30000. For 1 is 001. What you notice is that there's only the bits differ in only one position. So as you move along, there's a difference in bits in only one position. So if you look at 1 and 2, all the distances are the same, right? It's only in one position that the bits differ. Yeah? So the bits differ in the gray code. As you move from one number to the other, there's a difference in only one position, right? So if you look at the 4-bit gray code, for example, 0 and 1, there's a difference only in one position. All the other bit positions are the same, right? If you look, for example, between 8 and 9 for the 4-bit gray code, right, all the bit positions are the same except one position where they differ. If you look at the 13 and 14 again, for example, all the bit positions are the same except one position in which they differ. This is quite important if you want to be able to correct errors. And also when we do the Kano maps, we will need to use a gray code to represent the bit positions. There are a number of error codes that are used. There's a parity bit. In this case, a simple process of adding a special code bit to a data that improves its integrity, to improve its integrity. So for example, in the ASCII code, you have 7 bits that are used. Now what you can then do is add an extra bit to make it 8 bits, right? And then you count the number of ones or zeros in the message or the message that you want to send. And depending upon whether the ones are even or odd, yeah, you add an extra 1, yeah. So if you wanted to send the character S, for example, the character S is represented in ASCII as 10100011 using 7 bits, okay? When we code this for odd parity, Then we add an extra bit, yeah, because the number of ones in this, yeah, in the original one are 4. We want odd parity, so it means that there must be an extra one added. So there are 5 ones now in the. There are 5 ones now in the message we are transmitting. That's 1, 2, 3, 4, 5. 5 ones in the message we are transmitting. That's for odd parity. Now, for even parity, it means that the number of ones in the message you are transmitting will be an even number. So the parity bit is used as an error correcting or detecting code. So the idea is simple, that you transmit something, you count the number of ones in the message. So if any of them changes, then any of the bit positions changes, then you are likely to know. Because again, when the message arrives, you simply count the number of ones again and compare with what it's supposed to be. If it's not what, then it means that there's an error. So a few questions for you to consider. Try to convert to hexadecimal and then to binary the numbers shown. And then convert to octal, convert to hexadecimal, then convert both of your answers to decimal and verify that they are the same. And then also you can do the following sums, add the following numbers in using 2's complement to represent negative numbers. Use a word length of 6 bits, including the sign, and indicate if an overflow occurs. So the thing is to understand what an overflow is. So that brings us to the end of this session. Thanks for listening, and I'll see you in the next session.